Good afternoon, everybody. Thanks for making it this far. I promise to be exciting and long-winded. I have about 50 slides to cover. I'll go as fast as possible. I'm kidding. Ed Lawson, my colleagues Joe Hayes and Keith Sullivan, all from the Naval Research Lab. Before I begin, so we are machine learning and roboticist folks, not neuroscientists, and we're looking for neuromorphic approaches that we can put on our mobile robotics platforms to make some of our life a little bit easier. And towards that, let me introduce you to the problem of robot perception. So this is a really challenging problem. We've got a robot that's moving around real environments. Think about how hard it is to do autonomous driving. This is not autonomous driving. This is unstructured environments. Think about like, a robot going down a trail or something like that. We want the robot to be able to move and do other things like find people, but we also need to be able to move and not hit things, right? So we need to be able to efficiently make decisions from this stream of high-resolution images, which is just a lot of information to process. So we're trying to do this. Our target platform is Butch here, if you can see that picture over there. Butch is a little quadruped or robot. I've got a little bit more information on Butch later. But the idea with Butch is that it's a cat-sized robot that is intended to be backpackable. So think really small, think really lightweight, really low-powered, hardcore swap constraints. Towards our goal of using Butch to explore different environments, considering the following scenario, which we're going to explore in this talk. So let's say that we have an environment that we want to monitor. This could be the perimeter of a building, or it could be a trail or something like that. You give the robot GPS waypoints to go from point A to point B. But let's assume that I don't have a map available and I don't necessarily want to provide it a map. So how do I navigate from point A to point B? There's lots of different ways that I can get there, right? You could go through a muddy path or a sandy beach to get from point A to point B, but Butch is not going to make it on that sort of stuff. That's gonna end really badly. We might prefer the longer way, which might be a nice paved asphalt or concrete path between these outdoor waypoints. So this is widely varying terrain. There's lots of complex problems in natural environments. Some surfaces are better than others, as I mentioned. And Butch is really hardcore swap constrained. So we don't have the power. We don't have the power budget to put a GPU on there. So it's just not an option. So before I get too much further here, let me talk a little bit more about Butch. This is a lot of the work of my colleague Joe Hayes over there. So any questions about this, I'm going to redirect to him. But this was a part of the Mesoscale Robot Locomotive Initiative platform. This was originally intended to study robot locomotion on quadrupeds. So Butch here is from the NRL Scout, which is, I have a laser pointer here, well, whatever, which is from a secondary generation here. So Butch is hydraulically actuated, 3 joints per limb. The second generation, which they're exploring the problem of doing perception and other intelligent tasks on this platform, is equipped with a Z mini camera. So this raises the question of how in the world are we going to equip this thing with intelligence? So just like your cooking show, there we go, right? There's my finished pie. So this is the IBM TrueNorth processor. I assume everybody here is probably really, really familiar with this. From our perspective, we like it because it's very low powered. 1 million neurons, 256 million synapses, 4096 parallel cores. There's a streaming library that is available that can do inferences at thousands of frames per second. As I mentioned before, we're machine learning people. So what we've done with this is we've trained deep convolutional neural networks and used the Eden framework to convert these convolutional neural networks to spiking format to put them on this board. Okay. So, like I said, so I painted a nice pretty picture of navigating paths and stuff like that, but you got to start someplace, right? You got to crawl before you can walk or whatever. So our problem in the meantime, I have a laser pointer, is to navigate around. So this is the campus of NRL Washington, D.C., and there's sort of a nice little path around this campus here. So we want to have Butch navigate around this path here. along here. So this is a relatively simplified problem, but it does have some of the problems that we expect to see in the environment. So we're trying to identify, stay off the road, stay out of the grass, move along the path, don't hit things, don't run off the road. Before I have stuff on that later. So the way that we're doing this is we scan the region that's directly in front of the robot. We essentially fixate at 5 different locations here in front of the robot. And for each one of those regions, we crop a patch of size about 350 by 450. This is a huge input image for the TrueNorth, by the way. And we try to predict whether or not this is concrete, grass, or asphalt. So the goal is to stay on the sidewalk and don't get hit by cars. We think that would be really, really bad. And don't get on the grass. So the patch size is relatively big. So the way that we approach this problem is that we decided to let the TrueNorth decide how to resize it rather than providing the TrueNorth with a really tiny chip. So the first few layers into the network are relatively large convolutions with a relatively large stride length. You tell people in the machine learning community you've got a stride length of 11, they kind of look at you funny. But the thought here was that we could provide an intelligent way to resize rather than doing it on the board itself. Uses about half of the neural cores, 2284. This is fully supervised training. This is data that we collected around the lab, not on the path that we're trying to run on. And I mentioned Butch. So the Butch is in development right now. So our idea with this platform is we'd like to advance both the hardware and the software at the same time to shorten the amount of time that we can get this out and make this a usable platform. So our surrogate platform here is a slightly different robot. This is an Endeavor Robotics PackBot that has been equipped with a Carnegie Robotics S7. I'm providing somewhat preliminary status on this work. So what we have done here is the green area indicates paths. We started off right here. It can go to that point without any problems. It can go down here without any issues. It can come down here. And the red part indicates problems or areas where there's problems. So this obviously requires a little bit of logic here. I mentioned the GPS waypoints. So the first is that if it runs into a branching point at the crosswalk, it doesn't really know what to do. I was like, okay, I've run out of sidewalk. Should I turn around and go back, or should I go right, or should I do what? So that's the point where GPS waypoints are needed to provide the robot a little bit of logic necessary to advance. One of the more interesting bits is what do you do about crosswalks? So we really don't want the robot to get run over. I mean, the PackBot's actually a pretty rugged platform. I think it might be able to withstand it, but it's not ideal for sure. So this is another decision point. But there's kind of worse stuff here, which has kind of led us to wonder if you really can solve this problem entirely with supervised learning here. So this stuff is maybe kind of even mild stuff here, right? So this is area where it's seen some hard shadow from this fence here. So you can actually see what the robot, or what it's predicting here. So green it thinks is grass, and blue it thinks is concrete. So its preferred solution would be to get away from there and go on that teeny tiny patch of concrete that's closer to the road. Not what we want. The one on the right is this, sometimes you run across textures of concrete that are unusual. I mean, it could be a cracked concrete, or it could be something that's completely different here too. So there's 2 ways that you could solve this, right? I could either collect every possible type of variation of things that I'm ever going to encounter in front of the robot, got it? Or I could try to do something a little smarter, and I could try to maybe do some sort of unsupervised or reinforcement learning to try to give the robot examples of areas where it can go. Maybe it didn't know that it can go through this before, but I could tell it, no, wait a minute, you actually can traverse through that. So that's kind of an area those are sort of future work stuff. So wrapping up here, as of maybe a month ago, we got this fully integrated into the robot operating system ROS navigation stack with GPS waypoints. We've got a demo of the robot doing some limited navigation around the lab. We are working with the Loihi as well. We're sort of looking towards some solutions on the Loihi. Very excited about the tutorial tomorrow. And we've explored some other strategies here, foveation and fixation. I'm not presenting any of that stuff here, but that does show promise as well. So with that, that's the end.
Thanks, Ed.
Yeah.
There's a question over there.
Oh, yeah.
So you mentioned So really interesting presentation.
Thanks.
You mentioned the idea of unsupervised learning for a low swap platform. Did you have any thoughts or sort of ideas?
We're looking for suggestions from anybody that knows how to do this. I mean, it's some thoughts, but it's kind of mostly just ideas that we're tossing around at this point. I do think that's, I mean, I don't really know that there's any other satisfactory way. I mean, I'm not going to collect training data for every possible type of thing. I don't want to do it first off. Maybe I can hire some grad students to do it, but I don't think they want to do it either. But yeah.
Great, thank you.
Sure. Yeah.
All right. So I was just wondering, since you're using the TrueNorth chip and everything, did you look into any of these edge-based cameras that we saw presented earlier today?
Yes. Yes, I'm glad that you asked that, actually. We have a couple of DVS cameras there. The issue that we have with those is that color is a really important cue. The DVS cameras kind of lose color. So there's one of the problems. The other problem here is that when we go into like the forest, everything is an edge. There's events everywhere because there's trees and there's brush and there's other stuff here. And the robot just says, I just don't know what to do. We actually did a little bit of experiments on that, and it was not awesome. So I think it's a really promising approach, but I think we need to figure out maybe some of the other ways that we can filter that or something. Yeah. Oh, yeah.
Out of curiosity, with those. So just out of curiosity, have you tried using both DVS cameras and some sort of regular camera?
Yeah, I think
combining
that's kind of an interesting approach too. I mean, get a little stereo there possibly as well. We have not, but that's a great idea. Yeah. Okay.
Thank you.